Alright, let's take a look at question number 5. So for problem 5, we're going to find the limit as x approaches negative infinity of x to the third times quantity x minus 1 times the quantity 3x plus 1, all that divided by the third root of x to the sixth times x to the third plus 1. Okay? Alright, now if you take a look at this limit, how would you classify it? This is a limit involving infinity, okay? As an infinite limit where x approaches infinity. So whenever x is going to negative infinity or positive infinity, you want to look at the growth rate of the functions, and then that can help you determine the limit. Now, since we have a product of a factored form of a polynomial in the numerator, the fastest growing term in the expansion of that polynomial will tell us, will basically be the only term that we'll consider in the numerator. Same goes with the denominator. So what is the term with the highest degree in the numerator going to be? Well, it's what you get when you multiply x to the third by x and then multiply your result by 3x. Okay? If you want to waste time, you can expand the whole thing and take the first term, but we don't have time to waste, so we just want to be efficient here. So what we're going to do is multiply those terms. Why did I select those terms? Because in each factor, they have the highest degree. This factor stands alone as x to the third. This is the first degree term. This is the 0th degree term. So this, yeah, I'll pick x. And in this factor, 3x is the first degree term. This is a constant or 0 degree, so I pick that. All right. So if I multiply them together, I will have 3x to the fifth. 3x to the fifth in the numerator. Now in the denominator, the same procedure applies. I'm going to be taking the third root of the product of the terms with the leading coefficient in the factors in the denominator. So I'm going to take x to the sixth and x to the third. They are the terms with the biggest degrees in each factor. I multiply them together. That will leave me with the third root of x to the... Now what do you do when you multiply exponents with the same base? You add the powers, right? So it's x to the 9th. Let's simplify this further. We have limit as x approaches negative infinity of 3x to the 5th over the third root of x to the 9th is the same thing as x to the 9 over 3, which is going to be x to the third power. Okay, so now what are we going to do? We can factor out the constant, factor out 3, doesn't really play a role here. And then we're going to look at the limit as x approaches negative infinity of x to the 5th over x to the 3rd. Now, since we're going to negative infinity, what we can simply do is we can reduce this these two terms right here. So using the properties of exponents, whenever you divide in exponents with the same base, you subtract the powers, right? So x approaches negative infinity of x to the 5 minus 3, which is x squared. All right? Okay, now I can simply plug in negative infinity into this problem and actually calculate what the limit is going to be, but sometimes it's beneficial to first evaluate the sign before you plug in infinity. In this case, it doesn't really matter, so what I'm going to do is just carry out this substitution. So I'll have 3 times negative infinity to the second power. Notice that this square is going to impact this sign right here. So yeah, our answer is going to be 3 times infinity, which is equal to infinity. So that's the value of the limit of this expression as x approaches negative infinity. All right, let's take a look at question number 6. So for question 6, we have the function 5 to the negative x plus 6x to the third plus 5x over 2x plus 3 plus the natural logarithm of the absolute value of x plus 4. Alright, so for the A part, we're to find a simple basic function for the right behavior model. To find a simple basic function for the right behavior, or the right behavior model, the same thing. Okay, so before we go ahead and solve the problem, I need to go over two things real quick. First thing is the hierarchy of growth rates for functions. Let's put that on the side. You want to know that the slowest growing function that you're going to be dealing with, we're looking at as x tends towards infinity. Okay, so these are functions that are increasing. Ln x increases to infinity, but it's the slowest out of the growing functions. Next, we have the polynomial function x to the n, and then beneath that after that we have the exponential function a to the x, and then the fastest growing function, of course, is x to the x. All right. So as you tend towards infinity, this grows the fastest, followed by this, followed by that, followed by this. All right. Okay. Now let's also note the steps. The steps for finding the end behavior model are as follows. So first of all, you're going to take the limit as x approaches infinity of each addend. Okay, so find the limit as x approaches infinity of each addend function. So basically, all the functions that you're adding, you're just going to take the limit as x approaches infinity for each and every one of them. Okay, and then next, for the functions that approach infinity, you're going to compare their growth rates. Okay, so compare growth rates of functions that approach infinity. If a function goes to a constant, then that function is not a model for the end behavior, okay? Because it's just a constant, it doesn't count. We're focusing mainly on the functions that grow, and out of the ones that grow, the one that grows the quickest will be our right behavior model, of course, as x goes to infinity, okay? All right, so let's go ahead and do that here. So in this problem, we have three functions that are the addend functions. We have 5 to the negative x, we have 6x to the third plus 5x over 2x plus 3, and the natural logarithm of 5 of x plus 4. So let's look at the limits. Let's change the color here. So what is the limit as x approaches infinity of the first term, 5 to the negative x? This is going to be, let's see, we can reciprocate because of this negativity here. So the limit as x approaches infinity of 1 over 5 to the x. If we carry the substitution, we have 1 over 5 to the infinity, which is 1 over infinity, and 1 over infinity is equal to 0. Okay? All right. So this one, at infinity, this one doesn't really act properly. It actually approaches 0, so it's of no consequence. We're going to ignore that. Now let's take a look at the other two and see if they tend towards infinity. So for the next one, we're going to look at the limit as x approaches infinity of 6x to the third plus 5x over 2x plus 3. Okay, now if you look at this, since we're tending towards infinity, you just want to focus on the quickest growing function in the numerator and the denominator. So we have 6x to the third and 2x. Those are the functions that grow rapidly in the numerator and the denominator. So this becomes a limit as x approaches infinity of 6x to the third over 2x. And then when you divide this out, or you simplify it, you're going to have limit as x approaches infinity of 3x to the second power. And then when you plug in infinity, you're going to have 3 times infinity squared, which is equal to 3. I'm sorry, which is equal to infinity. Now what you want to do is you want to pay close attention to what the function looked like before you evaluate it. You see this entire function, we simplified it to 3x squared. At infinity, this entire function behaves like 3x squared. Okay? The ratio of the terms with the bigger degree in the top and the bottom basically determines how the function behaves at infinity. So let's pay close attention to this because this is the basic function that models the growth rate of this function right here. Now let's take a look at the next one. We want to look at the limit as x approaches infinity of the natural logarithm of the absolute value of x plus 4. Okay, so we can just do a direct substitution here. We have the natural logarithm of infinity plus 4, which is the natural logarithm of infinity. As you tend towards infinity, how does a natural logarithm function behave? It tends towards infinity, albeit slowly, right? So this is also infinity. So the first term doesn't really count. These two are the terms that go towards infinity as x approaches infinity. So now what we're going to do is basically compare the two functions. Which one grows faster? Is it this polynomial function here or the logarithmic function? At infinity, this behaves just like 3x squared, so we can focus on this. So which grows faster, 3x squared or the natural logarithm of x to the fourth? Those are the two we're comparing. If you go to our hierarchy, we can clearly see that the polynomial function, x to the n, grows faster than your logarithmic function. Logarithmic functions are like the slowest ones, okay? So in this case, the right behavior model is going to be given by this function right here, 3x squared, okay? So the right behavior model is 3x squared. So what does this mean? This basically means, let me state the significance of that. The meaning is that the limit as x approaches infinity of the original function divided by 3x squared is going to be what? Is going to be 1. That's what it means to be a right behavior or left behavior model, because if you take the limit as x approaches infinity of the function in that model, the growth rates are exactly the same, so it just basically becomes 1. So that goes the right in behavior model function. Alright, now let's take a look at the B part. For the B part, we are going to be looking for the simple basic function for the left-hand behavior. Okay, so for the B part, we're going to find a simple basic function for the left-hand behavior. Okay, left-hand behavior. So in the left-hand behavior, we're looking at the limit as x approaches negative infinity. All right, so which function will cause the quotient of the original function and that function to equal to 1 as x tends towards negative infinity? We're going to be using exactly the same procedure as we did earlier, but the only difference here will be that we're going to be approaching negative infinity as opposed to approaching infinity, okay? So let's go ahead and rewrite the original function we had, 6x to the third plus 5x over 2x plus 3 plus the natural logarithm of the absolute value of x plus 4. Okay, so now we're going to evaluate the adding functions to find the limit as x approaches negative infinity. So for the first one, we're going to do the limit as x approaches negative infinity of 5 to the negative x there. And then this, you can express this as the limit as x approaches negative infinity, reciprocate that of 1 over 5 to the x. And then we can do a substitution here. We'll do a substitution. We have 1 over 5 to the negative infinity. What on earth is this? Well, this is equal to 5 to the infinity. Because of this negative right here, it basically indicates reciprocation, okay? So what's 5 to the infinity? That rapidly goes to infinity. So this right here is a candidate to be considered. You notice for the right end behavior, right? That wasn't a candidate. It went to 0. But going to negative infinity, this actually is in the game. Okay? Now let's take a look at the next function. Limit as x approaches negative infinity of this function right here, 6x to the third plus 5x over 2x plus 3. We've done this before. We know that at infinity, just these two play a valid role. So we're just looking at the limit as x approaches infinity of the quotient of these two, which is 3x squared, as we did previously. So this is going to be 3x squared, right? And then when you plug in infinity by substitution, you have 3 times negative infinity squared. You see this square right here negates this, makes this negative a positive, right? So you just have 3 times infinity, which is just infinity. So this is also a candidate to be considered for comparison. Last but not the least, we're looking at the limit as x approaches negative infinity of the natural logarithm of the absolute value of x plus 4. Alright, so we can just substitute here. So we have the natural logarithm of the absolute value of negative infinity plus 4. So negative infinity swallows 4 up rapidly, so we have the natural logarithm of negative infinity, natural logarithm of the absolute value of negative infinity. So the absolute value does its job on the sign here. So this is just simply the natural logarithm of infinity, which is equal to infinity. So guess what? This is also a candidate for consideration. So all three of them are candidates for consideration. We have the exponential function, we have a quadratic, and a logarithmic function. So if you remember your hierarchy, which one grows the fastest out of the three? Let's go over our hierarchy again. We said that the slowest one is the logarithmic function, followed by the polynomial function or power function, followed by the exponential function, and then the fastest is x to the x. So if you look at this right here, this is the fastest growing one because it's an exponential function. All right. So let's go ahead and write down our answer. The left end behavior model. The left end behavior model is what is it again? 5 to the negative x. 5 to the negative x. Okay? Does it dominate? What does this mean? What is the meaning of that, considering the definition of what it is to be an end behavior model? The meaning of this is basically that the limit as x approaches negative infinity of the original function divided by 5 to the negative x, guess what that's going to be? That's going to be 1, because they basically match each other in growth rate at negative infinity, so their quotient is just going to be 1. Okay, so that's what it is to be a left-hand behavior model. So thanks so much for taking the time to watch this presentation. Really appreciate it. Do post a comment to let us know what you think about this clip. And if you have any questions, just put it down in the comment section. I'll be glad to address it. And also let us know what you think about this presentation. More clips can be found on mathcodeserve.com under AP Calculus. Thanks again for watching and have a wonderful day.